Hi, my name is Mohammed Hamza, and I'm a second year student studying computer science and engineering at RV University, Bangalore. And my project is the accelerated classification of nanomaterials using HPCC systems. And my mentor for this project was Dr. Vaishali Garai. Little bit of a background going into this project. I had recently taken part in a hackathon which was hosted by HPCC Systems in collaboration with my university, and we won that hackathon. So I have been exposed to ECL previously, and I was quite excited to work with ECL again for this particular project. Another thing that you need to know about me is that I'm quite passionate about machine learning. More specifically, its applications across different fields such as space technology or, in this case, nanomaterials. Moving to the introduction. So, recently there has been a rapid advancement in nanotechnology and nanomaterials research. It has a lot of applications which range from medicine and electronics to environmental protection. These materials have unique physical, chemical, and biological characteristics that distinguish them from the bulk counterparts. Vast amounts of unstructured data are available in the scientific community in the form of images within research articles, which make the extraction of meaningful data challenging for researchers. So, one of the use cases for this project is to help researchers classify nanomaterials. So, one of the problems faced by them is that they have to perform several tests to figure out what type of nanomaterials they're working with. And this project helps to reduce that stage of research. So various classes of nanomaterials have very specific properties, and that makes them applicable to specific industries. These images are crucial for identifying the type of nanomaterials. So the main aim of this project was to train a model powered by HPCC systems to help classify these materials. Moving on to overview, I plan to use a publicly available human annotated dataset specifically curated for the classification of nanomaterials from a technique called scanning electron microscope, or SEM images for short. So this technique basically extracts structural details of nanomaterials at a microscopic level. So the dataset comprises of 19,000 high-resolution SEM images, which are categorized into 8 different classes based on their characteristics. So some of these categories include porous sponges, powders, tips, biological and MEMS devices. So you can see some of these images on the right, and these were taken directly from the data set. So you can see electrons, fibers, and particles. So each of these categories encompasses a unique structural and structural detail, which is crucial for many different applications, specifically absorption, filtration, electronics, pharmaceuticals, and biotechnology. This data was taken from a research paper produced by NFFA Europe, and then it was pre-processed and prepared for training and testing. And all of it was done completely using ECL. An accurate and efficient classification model would facilitate in the identification and prediction of properties in new nanomaterials. And using HPCC Thor cluster workers would help in the acceleration of these processes. So one of the challenges, as mentioned below, is the time taken to manually test and figure out what type of nanomaterial researchers are working with. So using HPCC systems will be quite crucial for this particular project. Moving on to approach and methodology. So the general approach I followed revolved around using the GNN bundle alongside the Python bundle, which provides a parallelized interface to the Keras TensorFlow API. So as mentioned before, data was extracted from SEM images. Then we move on to data pre-processing. And some of the pre-processing steps included normalization and augmentation. Normalization of pixels, and augmentation was used to increase the variation of data by flipping by changing its orientation, etc., so that the model generalizes better on a wider range of data. Then moving on to model training. For this project, I used a CNN, which was created from the GNN bundle, and this model was used to process the data from images, and a feature map and pooling were created. You can see below that there is an example of a convolution filtering. So what happens at this step is that the model automatically extracts and learns features from the images such as edges, textures, and shapes, and etc. And then a pooling is created, which is then combined, and the original class is connected to that particular image. So there's also a code snippet which shows the model that we used. This is taken from the ECL. Moving on to results and evaluation. Since I'm working with separate classes of data, used categorical cross entropy as the evaluation metric, and accuracy was simply calculated by dividing the number of correct predictions with the true cluster. So the accuracy achieved was 89.41%, and this can also be improved and increased above 90% by hyperparameter tuning. More importantly, results show that using the HPCC GNN bundle working with the Thor cluster produced quicker results than using just the standard Jupyter notebook kernel. So, moving on to the resources that I use, I'd like to give a shout out to this particular GitHub repository. It had a specific file which showcased using GNN for MNIST prediction, and that had quite a bit to this particular project. For future work, one of the things that me and Dr. Baishali are looking forward to doing is creating a research paper for this particular topic. Furthermore, this can also be used, this model can be used, and a Roxy query can be created, and and the REST URL can be used to create a web application which can be used by nanomaterial researchers to upload their own photos, and the model will help them classify what type of nanomaterial they're working with. So that's about it. Thank you so much for your time.